Hello everyone, I'm Heng, and today I'm here to introduce you the mean value terms. The very first steps that I will introduce you how do we interpret the statements of MVT, the mean value terms. In the second, I will talk about the lemmas, which is the preparation before we start to prove the theorems. And the third steps will be the proving of the weaker version of it. So Rolle's terms is a weaker versions of mean value theorem. Then the very last part, I will combine both 2 and 3 together and prove the mean value theorem, the complete one. Let's step into the first step. What is mean value terms? Mean value terms is considered a very powerful function in the real world. Suppose that the function f is continuous and differentiable on an open interval AB. Then there exists a point x0 in AB which having the gradients of fb minus fa over b minus a. And we can say this value is exactly the gradients of a and b. The gradient is this value. In this a and b, we can draw a line which having this gradient. The gradient is fb minus fa over b minus a. And there exists an x0 in between a and b, in between here. Then we can find x0, approximate here x0, which having the exactly same gradients as the blue one. This is true for this case, the diagram and the function I show for you, but it also true for many cases. As long as it's continuous and differentiable on the open interval a and b, that it will work. So later, I will prove these theorems to you. Before I step into the proof, now let's have some preparation of it. We should prepare the lemmas. The very first lemmas is the additions of derivative. So if we took the derivative of f plus g, and it will exactly equals to the derivative of x plus the derivative of g. And the second lemma, we're telling that if this function is a differentiable function f, then the maximizer, a minimizer, will have the derivative of equal to 0. For example, here is the maximizer and here is the minimizer. It's having a flat gradient, which means that its derivative is 0. Here is the Rolle's terms. Rolle's terms stating that it's very similar to the mean value terms, but is having a restriction. A and B must equal to same one. So just now from the mean value term, we know that FA and FB may not be the same. So it is equal to minus over B minus A, right? But no, not in this case. Rolle's term stating that A and B must be the same, then there will exist a F0 in between A and B, which equal to 0. So maybe I show you a graph for easier to understand. For example, in this case, if A and B is the same, then there will exist a point in between A and B which having a gradient of 0. For example, here and here. How do we prove this? We'll split it into two cases. One is with maximizer or minimizer. And another one is without. In Rolle's terms, the first case we consider is having a maximizer or a minimizer. Having at least, we say, it can more than one, but having at least one. If we having at least one, we can say the points of the maximizer or minimizer, for example here, in between A and B, we're saying these points, the maximizer or maybe the minimizer, that point is exactly having the fx0 gradient of equal to 0. So that is stating in lemma 2 because every single maximizer and minimizer having the gradient of 0. So how about there doesn't exist any in between the A and B? Maybe you draw it out for easier understanding. If A and B, in between A and B, it doesn't have any maximizer or minimizer, means it's flat one. Since it doesn't go up or go down, so it remains the same all over the interval A and B. But this also shows us something. If it remains constant for the whole interval A and B, it means it's having gradient of 0. The flat graph is also having a derivative of 0. Every point in between here is having a fx of derivative of 0. Yeah, so it proven the case. Both cases, with or without, we cover all the functions of a continuous and differentiable functions in A and B. So this will show the Rolle's theorem is true. We will use these Rolle's theorems that step into the next steps, which is our mean value theorems, our final target of this video. Here, I will introduce you the idea behind the proof. Let's split in a function fx into two functions gx and lx. For example, here, at fx, why it cannot apply the Rolle's theorem? Because there are the 2 points are different, right? So here the fa and fb are not equal. When it's not equal, so we cannot use Rolle's theorems. So we try to modify the functions into something that we can apply as Rolle's theorems. How do we do that? We need the function lx. Lx is a linear function that connects the points fa and fb. So you see the connections that connects fa and fb. You also can say they have a characteristic of La equals to Fa and Lb equals to Fb. Yeah. And with these functions, we can modify the gx and on top of both as the fx minus Lx. It will make the functions that Ga equals to Gb. And we can apply Rolle's theorem into here, Rolle's theorem, into this function gx, then we prove back into the fx. So here is the idea, here is a draft. Let's step into the formal proof. So in the formal proof, we will consider the gx. We first define the function of gx. Then later, define the linear functions that connect between afa and bfb, the points. So maybe I draw a small diagram here. The L, this is the L, Lx, and the gx should be then the gx is the fx minus Lx. Okay, so we know that Lx is actually equals to it's actually a linear function. So we can write the functions is equal to mx plus c. Lx equal to mx plus c. And we can deduce the functions as shown as below. Yeah, high school stuff, so here I skip it. In the same time, we put this Lx back into the definition of gx. So we know fx is here and Lx is here, then just put the whole things into this part, into here. And then, so since we know both Lx and gx is continuous and is differentiable, which implies that gx is also differentiable and continuous. This by the lemma, the first lemma, gx is also continuous on AB and differentiable on AB. By calculating the value of Ga and Gb, we know that it's equals to 0. Since we already minus out, as the diagram show, as the graph show, Fa minus La, since it's the same, Fa minus La will equals to 0. And so GA will fall on 0, and the GB will also fall in 0. With these two values, the continuity and the differentiable, and also the value of GA and GB, we can now apply the Rolle's theorem into the G function. By applying Rolle's function, so now we already know there exists a x0 in AB such that its derivative is equal to 0. Then we take the derivative of this, take the derivative from the function itself. Let's list down the function of gx. Here is the gx definition that we just defined just now, and here is Lx. So now we take the derivative of both sides, and we know at lemma 1, then we get this function. And now we substitute the x0 into here, the x0 into the g prime functions. So we can calculate that the left hand side actually is equal to 0, like just now stated, since we applied the Rolle's theorem already, right? So the left hand side is equal to 0. But the right hand side, we can see that we have a f prime x0 and the gradients between the point A and point B, which is these gradients, FA and FB. Then we rearrange the equations and we can get the last lines. And this is exactly what we're telling in the mean value theorems. Like mean value theorem stated that is a function of continuous having the point A and B, which is differentiable and continuous in A and B. Then you can draw the lines. Then always exists a point like that, x0 here. So this exactly saying that the x0 in the x0 in the Rolle's theorem just now, the gx0, having the same property when it moves to the fx0. So when you put into the fx0, we just use the Rolle's theorem on the left hand side. Rolle's theorem on the left hand side. Rolle's theorem. And actually we just same as applying the mean value theorems on the right hand side. Yeah, there's a flow of there's a close relation between the Rolle's theorem and the mean value theorems. Here is the end of the proof, and thank you very much for watching this video. Yeah, here is the end. Thank you.